General Science says, welcome again to Science Lab. I am Al Renner. During the regular school day, I teach at Elliot Jr. High School in Altadena. And this is General Science, our symbolic space leader of the future. Today, General Science is going to take us to explore the wonders of nuclear reactors. And this is our guest, Dr. Robert Loftness, who is Chief Applications Engineer at Atomics International. Dr. Loftness, that's a division of North American Aviation, is it not?
Yes, it certainly is.
And this is Miss Doreen Melindy, our laboratory assistant, and her Model Science Fair project, which she is getting ready for the Converse Science Fair, which the applications have to be in for June 1st, do they not, Doreen?
That's right.
Dr. Loftness, I might say that some of the youngsters work hard and get good grades during the school and think they've done a good job. Some of them work hard and make a science fair project, do a little bit better. But Doreen has not made just one science fair project. This is your second,
No,
third.
my third.
This is her third, and she's done this one over twice already. She's
Very
the
nice
kind,
model.
certainly is, isn't it? She's the kind that doesn't give up, and I wouldn't be surprised one of these days if she comes up with a winner. We want to have you help Doreen a little bit on this again today, as you did last week. But before you do this, Dr. Loftness, I'd like to have both of you come over to see this chain reaction experiment, which one of the students set up for you. This is Bob McKeever. Won't you come over here, Bob? I almost set that off there, didn't I? Bob has made a classroom edition, you might say, of Walt Disney's famous chain reaction experiment. Walt Disney had a gymnasium full of mousetraps, I believe, and one neutron set off two, and two set off four, and on up the chain reaction. And I'm going to ask Bob to drop in his neutron in his little hole here and set off this chain reaction experiment for you.
Well, it certainly works, doesn't it?
Now, that's an instantaneous reaction, isn't it? If there ever was one. Well, today we're going to talk about nuclear reactors, and a nuclear reactor is the same thing in a controlled way. It's kind of like a slow motion chain reaction, isn't it?
Well, the same sort of chain reaction occurs in nuclear reactors.
Thank you very much, Bob. And we'll go back to Doreen's project here. Doreen has been having a little trouble since we came back from the time we visited you at the Atomics International plant. As I said, she did this twice already. She's pretty good in the shop. I haven't seen many girls who could take drills and saws and work like this. She worked that core of the reactor out on the lathe all by herself. And she had trouble getting these rods through here, and she wants to ask you a few questions about that today, if you can take time to do that.
I'll be happy to answer them, certainly.
Dr. Loftness, the one question that's really been bothering me is where are the isotopes put in?
The isotopes in general are placed in these 5 tubes, which are here in the center and pass directly through the core. They go from one side of the reactor to the other. Your nuclear chain reaction, of course, is occurring in this center, which is filled with a water solution of uranyl sulfate. Down below we have some other thimbles in which we put instruments to detect the power level and the number of neutrons being given off by this nuclear chain reaction. And these things around the outside all represent different shield areas. We have to shield this nuclear chain reaction because of the radiation that occurs. And we use lead and paraffin and boron in these various shield areas. And outside of that comes ordinary water.
Dr. Loftness, it's a little bit like this reactor is giving off an invisible light, isn't it? That might give a person a bad case of sunburn?
It certainly would, yes, if you were too close
and
to it.
What kind of shielding do you use in the inner cores? Each one of these is an inner core with a protective substance in it.
These are composite shields here. Some of them are lead, others are made up of paraffin and lead, others are boron and paraffin. And between this and the tank itself is ordinary water. The radiation level outside the reactor, of course, is below the acceptable level for radiation tolerance established by the Atomic Energy Commission.
Well, when you put in the isotopes, which Doreen is asking about, just where do they go in? And
well, they go in through these tubes here. They are irradiated for a length of time, which depends upon the particular isotope. And they have a great many uses in many different fields. One of them, we use phosphorus 32, which is a very important plant nutrient. They add phosphorus 32 to fertilizer, and then they measure the radioactivity in the leaves of a plant to determine whether this fertilizer is being adequately used.
I have a friend who grows oranges, and he knows exactly how much fertilizer to put on a plant. Now, I bet he's been out to your plant to find out about this, hasn't he?
He may have been, yes. It's certainly true. Another use of isotopes has had much publicity during the past 4 or 5 years, and that's the use of carbon-14 for dating historical events.
That's like when they find a caveman's fire?
Right. Carbon-14 is a natural radioisotope made by the action of cosmic rays on nitrogen in the atmosphere. And this nitrogen changes to carbon, which becomes carbon dioxide, which is absorbed in plants, and ultimately winds up as wood or other plant material. And after this carbon-14 decays slowly in activity, and you can measure its activity and count back and determine how old a particular mummy is or any particular thing you want to dig up out of the ground.
That's pinpointing prehistoric time pretty much now, isn't it?
It's also used for other things, such as determining the blood flow in the body. You can drink a solution of ordinary salt, which has a radioactive sodium atom in it, and you can follow the course of the blood and pick it up in the tips of your fingers. Actually, this occurs usually in about 30 seconds. You can pick up all these radioactive
I know in
materials.
teaching biology, we talk about drinking milk and making bones and teeth. You just don't say it now. You can say they can watch it go right around the body and end up in the bone, can't you?
This is certainly right, yes.
But Dr. Loftness, do you remember when you first invited Doreen out to see this? They took some movies of her controlling the reactor, and the studio has those movies today. Would you like to see them?
I certainly would,
well,
yes.
Let's zip from Science Lab out to Dr. Loftness' lab at Canoga Park and see that research reactor. And I believe there we are coming up. Are we coming up to the entrance?
Right.
And just about to go in the door there, aren't we?
Well, this is the main entrance to our plant in Canoga Park. We'll be going inside of the building to see what we call the laboratory reactor. This reactor has a number. We call it the L77. The reactor is...
That's the same one that Doreen has modeled here.
Yes, it's the same reactor which Doreen has made a model. It's a small reactor, but it's located directly in our office and laboratory building. It's a very safe reactor. Here I'm showing you taking apart a film badge, which we use to monitor the radiation which an individual receives. Inside the badge are a couple of pieces of metal which screen off various types of radiation. So you can tell whether it's alpha, beta, or gamma radiation.
Do you develop these right away?
We develop these badges once every week, and each individual who's in a room of this sort with a reactor must wear a badge, and our health physics group collects these once a week and develops them to see whether or not an individual has been overexposed. As far as I know, in the entire history of our laboratory, nobody has ever been overexposed. Well, this is the control console, which Dick Johnson is sitting there. A panel of instruments which is used to observe the operation of the reactor. He has his hand there on a switch which runs the control rods in and out. I think he's running the rods out at the moment to start the reactor up. And he's pointing to a meter which indicates the power level.
He was going to show Doreen how to operate that, wasn't he?
Yes,
about that time.
He was trying to show the general operation of the whole reactor. There are other types of instruments on the panel. Excuse me.
Does that take very much education to be able to run one of those?
No, it takes some education, certainly. The reactor operators are normally high school graduates. Mm-hmm. Now, this is a sample holder. We're placing foils in this, and this will be placed in the reactor.
And this is an isotope slug, isn't it, Dr.
Yes,
Loftness?
this is the sort of thing you use to produce isotopes. We are using, in this case, foils of cadmium. These are placed in the center of the reactor, and the neutrons in the reactor make this material radioactive. So when you take it out again, you can use it for various purposes. You do the same thing if you were going to irradiate almost any material.
There's Doreen putting the isotope slug into the slot, you don't call it a slot, you call it the tube?
This is a central exposure tube.
Central exposure tube.
Could you tell me just what an isotope is, generally?
An isotope is a somewhat difficult expression, but it's one form of a particular atom. atoms have sometimes 2 or 3 different types of isotopes, depending upon the number of neutrons they have in the nucleus.
Each isotope has a different weight, doesn't it?
Each isotope has a different weight, yes.
There's Doreen taking the, that's just like a Geiger counter tube, a Geiger-Müller tube, isn't it?
Yes, this is a Geiger counter, a Geiger-Müller tube. She's measuring the radiation outside the tank there. We have one of these constantly on the outside to measure the radiation level. Well, Dick Johnson here is bringing the reactor up to power to irradiate these particular foils. He's pointing out there, I'm saying, several of the instruments used to control the reactor. All the instruments on these reactors are designed such that if something goes wrong, it automatically shuts the reactor down. They're all called fail-safe. They will fail safely in any event.
We find that through industry. Things are quite automatic these days, aren't they, and quite safe.
This is a common procedure in industry, yes. Particularly common with nuclear reactors.
Doreen operating that scram button, that name was interesting to me.
Yes, there is a button on the reactor which the operator can push to shut the reactor down manually.
I remember she did very well, except that she scrammed those rods to the bottom when there was a big boom.
Yes, it makes a bit of noise when the rods drop in. The reactor is actually controlled by moving 2 neutron-absorbing rods in and out of the reactor vertically from the top. That's the scram button there. It's really the shutdown button.
What does that? Oh, scram means shutdown.
It means shutdown, yes. Well, after the samples have been irradiated, you take out first the shield plug, which is put in, and then finally the sample container itself.
There she's using the Geiger tube again.
There, we're monitoring the radiation level of the samples.
I remember that was quite warm as it came out of the reactor, wasn't it?
Yes. Some of these samples come out quite warm and must be handled at quite a distance. This reactor, because its power level is fairly low, does not produce a tremendous amount of radioactivity, so it can be handled usually with a pair of tongs. But some of the higher powered reactors do produce very active isotopes that must be shielded in heavy lead casks.
He's taking the tongs there now, isn't he, to take that out?
Taking the sample over to the table where we take it apart again, and after we let it cool down for a while, the radioactivity decays away, and then we measure the activity in the foils.
But Dr. Loftness, that is a typical research reactor, isn't it? And you are selling these to industries and universities. Right, yes. And how many of these have you made and sold already?
Well, we have built some 6 of these. As a matter of fact, the first one of this production model went into operation just the first of this week, and it's been in operation every day during this week. We have 5 more which are in production, which will be sent out to various universities, both here in this country and also in countries abroad. We plan to have one of these over in Geneva, as a matter of fact, for a big exhibition there in September. It'll be an operating reactor in the exhibit itself.
Good.
Dr. Loftness, is there very much of a difference between a power reactor and a laboratory research reactor?
But Doreen, before we go into that, could I show you something?
I'd certainly like to.
We have a lot of students here who I think would like to see Doreen's research.
Right, I'd like to see it myself.
In these science fairs, a lot of times it's research that pays off. Anybody can make a model, but let's see, I want to get your science section, Doreen. Doreen has been doing quite a bit of research, getting ideas together for this. You can see that she has thought her problem out, and she has listed the problems she's working on, the various parts of it. And then she's kind of outlined the procedure, and I'll just go through her illustrations here. This is the thing I like best. It's nice to see a student come into class organized like this.
Right.
It just makes it nice to work with them. Doreen has this little technique used at a lot of the universities and high schools where you put your ideas out on various cards, and you can put them into piles like this as possible chapters. And you can be a little creative because you can change your paragraphs around this way. You don't have to write it just as some book said it.
Well, it's a very good organizational technique.
We as teachers like to see students gather all the possible ideas, and you as scientists like that too, don't you? And then as they have all the ideas before them, to pick the best ones and write those up and even throw some of these away and discard them.
Right.
That's what we like to see. And then also, I'd like to show you another idea that really pays off. These are little models that save students a lot of time in these science fairs, Dr. Loftness. Doreen has several ideas here for building this up. Now, this is not complete. As I said, she has done the shop work on this twice already.
Right.
And she just might do it again. I don't know. I don't think she's looking forward to doing anything like that. But she has these possible layouts, and she can work from these and compose them, change them around without buying a set of materials, worth of materials. And then when she has it planned, this is an inch to a foot. She can go out and buy the right amount of materials, and she's in for a good project, she knows.
I think it's a very good idea, Rudy.
I think a lot of the youngsters would probably enjoy doing this more if they could just work with it, be a little bit more creative with it. And now this was a research reactor, wasn't it?
This is right.
And you're also very much interested in power reactors at Atomic International, right?
This is true, yeah.
Well, you brought this very nice model of a power reactor. This is your sodium research reactor. And we have a film of Doreen, you showing Doreen around this a week ago Saturday. And by film clip, let's zip up from science lab to your laboratory again, shall we?
Fine.
And then would you take it? This one's at the top of the hill, is it not?
This is right. This is in the Simi Hills up above Canoga Park.
All right, now here we are in the car, going up the road there, and that's where those cowboys have made a lot of those pictures in those rocks, aren't they?
Yes, this has been a great spot for making cowboy films. This is the entrance to our Sodium Reactor Experiment area. This is a large power reactor experiment. It operates at some 20,000 kilowatts of heat. As a matter of fact, this reactor achieved full power just last evening.
I think I read something about it in the paper today as we were coming over here.
You may have heard it on the radio today.
It was a newscast, I believe.
This is right.
Isn't it serving its power for the Edison Company?
Yes, the Southern California Edison Company does have a turbo generator unit, steam boiler, which they operate, and this produces power for Southern California.
That's the company right next door at the top of the mountain there, isn't it?
Here we're getting these film badges again, which must be worn in the neighborhood of any nuclear reactor installation. These are the control rods on top of this sodium power reactor. The reactor itself is below floor level and extends down some 25, 30 feet below the floor level. These rods move up and down in these casings. These are neutron-absorbing rods, which either start the reactor up as you pull them out or shut it down as you reinsert them.
You must have a lot of cement or lead casing around them for protection, haven't you?
Yes, the radiation shield on top is about 6 feet thick, made up of extra heavy concrete. These rods have their motors on top. The reactor itself consists of a whole nest of uranium rods around which we have some graphite, and then we use sodium to remove the heat from these rods as a nuclear fission occurs. People working on top of the reactor put on these shoes, and these shoes are not to protect the people, but to protect the reactor and keep dust out of these holes that were visible on top in which the fuel elements are inserted.
I was wondering why the tops were colored circles, and I couldn't tell if they were on the reactor or not.
Well, these little plates they put on top of the various fuel element channels indicate...
Looked like somebody was about to play shuffleboard.
Yeah, it indicates what sort of material is in that particular position. One color indicates fuel elements, another color indicates a control rod, another color indicates an instrument thimble. Some colors just represent blank spaces. And this way the operators know what they have in which position.
Those were pretty big boots for Doreen, weren't they?
Yes, I think these are not designed for small girls. This is the fuel element transfer cast. These elements, after they're removed from the reactor, are extremely radioactive and must be withdrawn into a shielded cask. And this has lead shielding around it, and this is the outer...
That's a giant lead tube.
It's a giant lead tube.
Nothing looks like it weighed several hundred tons. I'll bet it does, doesn't it?
It doesn't weigh quite that much, but about 60 tons, yes.
It was heavy.
And it moves along on an overhead crane. The elements are drawn up into this thing from the reactor and then are moved over to a cleaning area and then to a storage area where they're stored until some of the energy has decayed and they can be handled a little more conveniently.
Doreen didn't know she was going to be a crane operator that day,
No,
did she?
no,
No, that was fun.
This is your control room for the reactor, isn't it?
Yes, all the instruments to monitor, to control the operation of the reactor are located in this particular room.
The fellow who was sitting at the control desk surely looked young to me. Do you use young men in your organization?
Yes, all these operators are fairly young fellows. All they need is a high school education with some major in science. This chap Dick Phelps is one of the reactor operators. We normally have 3 operators plus a chief operator on each shift. This reactor runs around the clock 24 hours a day and 7 days a week.
In other words, once you warm it up, you keep it going. For instance, this week you started it again, and it will go for some time then.
Well, it's been running at lower powers for some time, and we just brought it up to full power last evening. These are some of the meters which indicate the positions of these control rods, which move in and out of the reactor to either stop this chain reaction or let it proceed. And the buttons and the levers you push either move them up or down. There are little meters on there that indicate the exact position in inches of each rod. All the meters in the back indicate any number of things, the temperatures and the pressures and the flow rates, neutron level, and this sort of thing. But this is the nerve center of the entire reactor installation. This is where it's all controlled. This control desk in the front has, in a small way, some of the meters that are larger on the back, so that the operator has a direct view immediately in front of him.
He has a full control then of heat, pressure, and all those things. And if anything gets too warm, the pressure too much, it automatically takes care of itself in an instrument like that, doesn't it?
This is correct, yeah.
Those were strange-looking Geiger counters. One was almost like a gun.
Yes, these all are instruments to monitor the radiation level. There are 3 of them there on top. One is called has the name of Cutie Pie, and this is the one. This happens to be Juno here that you have, and it has a door in it which can shield out the various types of radiation. You can measure either gamma or beta or alpha radiation. This one is called Cutie Pie, and this measures beta and gamma radiation.
Well, which type of radiation is most serious to the workers around there?
Gamma radiation is normally the most serious radiation.
Penetrating.
It's the most penetrating of the 3 types of radiation, and it's the thing we're looking for. This monitors the number of neutrons that are escaping from the reactor. It's a fast and slow neutron monitor, and this picks up and tells the number of neutrons. It's really only the fast neutrons that have any real effect. Again, these are used only as to monitor. We've never had any overexposure of individuals, and this is the purpose of having these things, is to make sure that nobody is ever overexposed.
And then you had a gentleman who followed Doreen around, and you around too, most of the time, didn't you, just to keep an eye on things?
They try to do this all the time, yes.
A health physicist, I believe you said he was.
I noticed you had a sort of TV there. Could you explain that?
We use a TV camera there. We have a camera down below looking at some of the components below the floor, which are very radioactive, and we can view them here without being exposed to radiation.
Oh, this was fun. Remember, Doreen spent half an hour on this, I think. What did you call that? That had a long name.
This is called a master-slave manipulator, and it's a device whereby you can handle highly radioactive materials with some semblance of using your fingers. It tries to imitate your finger motion inside with the motion outside. And here the technique is shown for lifting out a container out of a shielded cask inside of what we call a hot cell. Actually, Doreen is looking through about 4 feet of lead glass into this particular hot cell.
That's interesting that there was so much lead in that glass. I think I heard one of the technicians say that was 60% lead in that glass.
It's about 60%. You can still look through it, but it's very good protection against radiation, and this is the reason it's used.
Those are really a lot of fun to operate.
I tried it for a few minutes, and I felt that my fingers were about 6 feet long, and I was reaching way into that hot cell of yours.
It's really quite a technique for using these things.
Well, that makes it very safe for handling and
Right.
pouring and
Right, this is-
working with your materials. That invisible light, you might say, gamma radiation, is quite a problem, isn't it? When you can't
Yes,
see it, it's
it certainly is.
a little hard to
yes.
work with sometimes.
Well, these two sets of rods,
They look heavy.
they are heavy. One of them, one set is made of steel, and the other set is made of uranium.
Did you tell the difference, Doreen?
Yes, the uranium seemed a lot heavier.
Uranium is
About the heaviest thing I picked
it's
up.
over twice as heavy as steel. This is what is called a hand and foot counter, and this counter is used to monitor the radiation on the surface of the hands and feet as a person is leaving. And to illustrate the operation of this, Doreen is going to put my watch, which has a luminous dial on it, into one of these chambers here to indicate that something does happen if you do have radiation there. The lights flash up on the outside of the right hand there. Ultimately, a sign comes on that says decontamination required. And when this sign comes on, then you have to go find somebody who will do something about it. A health physicist has an office right next door.
He
So
takes
there's
care
no
of you.
problem,
Looks
no.
like Doreen was safe according to that sign.
She was safe according to that sign, yes, but you can check these instruments by using isotopes such as you have in your...
This is our last view from the hill, wasn't it?
This is a view of the entire installation, the reactor building, which is a concrete building. The reactor's inside of this. Then off to the left here, there are lines coming across which indicate are for sodium. The left-hand side is the turbo generator and the generator set.
This is it. We're back from the film now,
Yes.
and we're right in the studio, and this is Dr. Loftness' very fine model. We're right at about this spot where the camera the last time
Yes,
went.
we're looking at the same thing. I might start on this side, indicating...
Would you
things-
just point these out, Dr.
Right.
Loftness?
The things we saw first, during the film, we did see this fuel transfer cask here. The reactor core is under the floor at this point, underneath. This hot sodium, which gets its heat from the nuclear fission, comes out in pipes over to a heat exchanger, which gives its heat up to more sodium, which comes out through these pipes here over to a steam generator, where we boil water and produce steam, and the steam then is transferred over to the turbine generator on this side, and then the turbine generator runs a generator here and produces electric power.
And the Edison company picks up that power and distributes it all over Southern California, doesn't it?
This is right, Southern
I was
California,
surprised to hear
Edison.
that. Well, Dr. Loftness, I surely stand in awe of you nuclear scientists and your profound knowledge of all this invisible business that goes on under the floor. And I think that, Doreen, don't you think that he's put it down on our level very
Yes,
ably
I
today?
do.
Well, it's surely been a pleasure to have you with us.
Thank you very much, Mr. Renner.
Dr.
It's a
Loftness,
pleasure.
if you'd like to look in next week, we're going to have a program about electronic computers. And we're going to have a 5th grade boy who made a small computer to do his homework. And I think it'll be a very nice thing on the program. I hope that all you folks will be with us next Thursday afternoon, 4 o'clock, here on Good Channel 13. We're going to have a very fine program for you. Good afternoon.
This has been Science Lab, today featuring Mr. Al Renner through the courtesy of the Pasadena City School District. Science Lab is presented by the Office of the Los Angeles County Superintendent of Schools in cooperation with the school districts of the county. This has been a KCOP Education and Public Affairs telecast. Next, Bingo at Home.